How does kinetic theory link microscopic motion to macroscopic gas properties? Imagine watching tiny invisible balls bouncing around inside a balloon. These tiny balls are molecules, and their movement explains how gases behave on a large scale. The kinetic theory of gases helps us understand this connection. It shows that the random, constant motion of molecules directly influences properties like pressure, temperature, and volume. When molecules move faster, they collide more forcefully with the walls of their container, which increases the pressure. If molecules slow down, the pressure drops. The theory models gases as a huge number of small particles, each moving independently and colliding elastically, meaning they bounce off without losing energy. These collisions are what create the pressure we measure. The size of molecules is tiny compared to the space between them, so gases are mostly empty space. This allows gases to expand and fill any container. Temperature is directly related to the average kinetic energy of the molecules. When temperature rises, molecules move faster, and their kinetic energy increases. This explains why hot gases feel more energetic and exert more pressure. The theory assumes no forces between molecules, which is true for ideal gases. This simplifies calculations and explains why gases often behave predictably under many conditions. The collective behavior of trillions of molecules moving and colliding results in the properties we observe. For example, pressure is caused by molecules hitting the container walls, and temperature reflects the average energy of these molecules. This understanding helps us calculate how gases will act in engines, refrigerators, or in the atmosphere. It forms the basis of the ideal gas law, which links pressure, volume, temperature, and the amount of gas through the equation PV equals nRT. Here, P is pressure, V is volume, T is temperature, N is the number of moles, and R is the gas constant. By knowing how molecules move at the microscopic level, we can predict and control the behavior of gases in many practical situations. This connection makes thermodynamics more straightforward and rooted in the physical motion of tiny particles.